This lecture is going to be based on derivatives of polynomials, the definition of derivatives. We'll be using f apostrophe with respect of x equals the limit of h approaches 0 with f respect of x plus h minus f to respect of x over h. We have known this as our instantaneous rate of change, slope of a curve, or a slope of a tangent line. But for this purpose, we'll be using it as our derivative. Our notation will be f to respect of x will represent our function, and f apostrophe x or d over dx will represent our derivative. Before we jump into polynomials, we will start with the constant function. F to respect of x equals c, our constant. Using a formal proof of the definition of derivative, we have the limit of h approaches 0 with c minus c over h, with c or being our constant, equals 0. Now taking the limit of 0 as h approaches 0 equals 0, which means that any derivative of a constant by itself will be 0. Derivative of a constant. Another way to prove it is by looking at the graph. We're having the function of f to respect of x equals c, or constant, which is the line of y equals c. In this case, our constant has the slope of 0. Now we have samples of a constants. We have the derivative of 31 pi equals 0 and the derivative of 3e squared equals 0. We have the derivative of square root of 1/2 equals 0. Due to that, pi and e are not variables and they're also numerical. These are considered a constant. That is why we have them equal to 0. Even though you're multiplying them, it still equals 0 given that it's a constant and not a variable. Derivatives of a function. Before we move on to the power rule, we should be able to derive the function itself. That's why we have that x squared, and x to the third power as our functions. As we derive, there should be a pattern in our answers. As you can see, the derivative of x is 1, the derivative of x squared is 2x, and the derivative of x to the third power is 3x to the second power. Power rule. If n is any real number, then the derivative of x to the power n equals n times the power of n minus 1. As proven before, the derivative of x to the third power equals 3 times x squared. Using the power rule, we're able to get the same answer without having to use the definition of the derivative. The constant multiple rule. We have our proof, which is g respect of x equals c, or constant, times f with respect of x. By using the definition of derivatives, we have g apostrophe respect of x equals the limit of h approaches 0, as g respect of x plus h minus g of respect of x over h equals the limit of h approaches 0, as c, or constant, is multiplied by f of x plus h minus f to respect of x over h. We're able to take out or factor out c, or constant, out of the equation on top. Therefore, when we take the limit of h approaches 0, we're able to take our c constant out of the function by using the limit law of 3. This is why our answer is c, or constant, being multiplied by the derivative of x. Our examples are the constant multiple rule, which are the derivative of 3x squared, negative x to the second power, 1/2 times x to the fourth power. We're able to remove our constants, which are 3, negative 1, and 1/2. Then we use our power rule to get our derivative, which is 6x, negative 2x, and 2x to the third power. The sum rule. Since we have capital X respect to x equals lowercase f respect of x plus g of x, we'll be using the definition of derivatives in order to prove the sum rule is actually valid. Now, as we have the limit of h approaching 0 of capital F respect of x plus h minus f respect of x over h equals the limit of h approaches 0, we have f lowercase f respect of x plus h plus g of x plus h minus f of x plus g of x over h. As the limit of h approaches 0, we start dividing the functions or grouping the two functions into two separate equations. Now, since they are separated, we are able to take the limit of each function, which equals or f prime of x plus g of prime of x, which are the derivatives of each different function. Thanks to the limit law, we're able to do this. The sum rule has two notations. We have d over d of x of f respect of x plus g of x equals d over d of f respect to x plus d over d of x with g respect to x. We also have the prime notation, which is f plus g with respect to prime equals f prime plus g prime. The difference rule is the derivative of x with respect of x minus g with respect of x. Now, using what was applied before with the sum rule and the constant multiple rule, we're able to get this formula of d over d of x of f respect of x minus d over d of x to g respect of x. As the notation noted down below, we have f minus g, then it becomes f plus negative g, then f plus negative 1 times g. We're able to apply this in our difference rule, meaning that we don't have to prove it as we did with the sum rule. Do a sample 1, we're going to be using our rules that we went over, the power rule, the constant multiple rule, the sum, the difference, and the constant rule. For our sample 1, I wrote in blue our constants, so it would be easy to differentiate between our variables. I'm going to start deriving from our left to right. So I'm going to start writing it down. Or do it a little bit bigger since I did it too small. And I'm going to do it by parts in order for us to be easier to differentiate between each variable. I'm going to write the constants in blue. I'm going to keep that. Okay. D over dx, x to the 4th power, plus, we're using the constant multiple rule, we separate 2, then it's going to be d over dx of x squared minus over d over dx of our constant 5. I'll let that be blue since it's just a constant. This could be x 8. This could be 7 thanks to our power rule. Remember, our power rule is n minus 1, and we move n to the side. So as we keep going, 12, which is multiplied back in, this is going to be 12 times, brought down to 6, x to the 5th. We're going to do the same thing for this one. Bring it down to 4, it's going to be 4 minus 1, which is 3, 2 times 2, x to the 1st power. And remember, when it's a constant, it just goes to 0. So now we have to multiply this together. So it's going to be 12, 1, 72, x to the 5th, minus 16, x 3rd, plus 4x. And these are final answer for our derivative of our polynomial for. So now for this problem, we're multiplying two functions together. Before we even start, we're going to multiply this function with this function, so it'd be easier for us to derive. We're going to multiply our polynomial. So it's going to be 6x to the 3rd power, b plus 2x, plus 3x to the 2nd power, and it's going to be 1. We're going to fix this to be in the correct order, so our notation is not all over the place. Now that we've done that, we're going to derive, and we're not going to forget our notation, our d over dx, and if it's easier for you, remember the constant multiple, you can separate it and just do d over dx, x to the third power plus 3, your constant, times d over dx, second power, plus 2 times our d over dx, x, plus our derivative of constant 1. Now that we have that, remember, do a power rule right here, this one as well. This one goes to 0 because it is our constant. So it's going to look like this, 6 times 3 x to the second power plus 3 times 2 x plus 2 times 1. Remember our sum from before, our derivative from d over dx of x will be just 1, and this is 0. Still include that so we don't forget. 18 x to the second power plus 6x plus 2. And this is our derivative when we're multiplying two functions together. So thank you for watching my polynomial derivatives lesson. Please subscribe, like the video,